First is absolute error, which is the modulus or the magnitude of the difference between the true value and the actual value. Now, since it's modulus or the magnitude, it doesn't matter if I do true value minus the experimental value, which I'm calling as actual value here, or if I do actual value minus the true value. The order doesn't matter here. Then we talked about the relative error, which is the absolute error divided by the true value. Lastly, we looked at the percent error, which is the absolute error divided by true value. That means the relative error multiplied by 100%. All right. So we're going to use these formulae to solve the problems that are coming up next. First problem, the value of g. My favorite acceleration due to gravity on the surface of Earth is measured 5 times, and the results are 9.79, 10.03, 9.98, 9.67, and 9.83 meters per second square. What are we asked to do? We are asked to compute the mean value and the relative percent error of experimental g. Very well. The mean value of the experimental value of g. G bar will be equal to 9.79 plus 10.01 plus 9.98 plus 9.67 plus 9.83 divided by 5. I know that this is a very easy problem, but we have to first go through easy problems to make it to the harder problems. 49.28 divided by 5, and this is still in meters per second square. Let me divide this answer by 5 and we get 9.856 meters per second square. Now look at each of these individual values of g. They have 3 sig figs. And not just sig figs, they are to 2 decimal places. So our final answer must also have only 3 sig figs and should be to 2 decimal places. When we round off 9.856, what do we get? Our answer is 9.86 meters per second square. Next, we are asked to find this is the mean value of the experimental g. All right, here experimental g. Next, we're going to find the relative percent error of experimental g. All right, relative percent error is going to be absolute error divided by true value times 100%. Okay, so absolute error will be 9.81 meters per second square minus 9.86 meters per second square. Absolute value of this difference divided by true value of 9.81 meters per second square divided by 100%. What do we get? So 9.81 minus 9.86 is negative 0.05. Since we're taking the absolute value, we get 0.05 meters per second square at the top, divided by 9.81 meters per second square at the bottom times 100%. So what happens to the units? The units meters cancels meters, second square cancels out. Our answer is going to be 0.05 divided by 9.81 times 100 gives us, okay, do I have room here? 0.509%, which can be rounded off to, if you want 2 sig fig, it will be 0.51%. You want 1 sig fig, you can round it off to 0.5%. So this was a fairly easy, fairly simple problem just to build foundation. We're going to move on to harder and harder problems as the lecture goes on. We're going to carry this forward and talk about how to write this experimental value of g in its proper form. What do I mean by proper form? By proper form, I mean that the answer is written as average value of G experimental plus minus this delta G experimental average. So this delta G, let me not actually write let me not write average here yet. So this delta G, this is the uncertainty in the value of G that is measured. Some people might call it as error in the measurement of G as well. Now, how do we calculate this G delta? Now, the question is, how do we calculate this? What is this delta G experimental? A very primitive way to do it will be to find the range of the data and divide it by 2. And that is your delta G. So for this case, to find the range of the data, we'll find G max minus G min and divided by 2. So in this given data, what's the highest value of G? 10.01. And what's the smallest value? 9.67. 10.01 minus 9.67 divided by 2. And this gives us, all right, to go from 9.67 to 10, it is 0.23 and go another 0.01 to get to 10.01. So that is going to be 0.24 divided by 2, 0.12. So the answer in the proper form will be 9.86. We did this on the previous slide, plus minus 0.12 meters per second square, which can be further written as 9.86 plus minus 0.12. I have factored out the units out. So this is my actual answer in the proper form, where I'm writing the average value of G that is measured plus minus the uncertainty in the average value of G. Does it make sense? Now, like I said, this method of finding the uncertainty, this is the most crude, most primitive, and the easiest method. There's another method to find the value of G. And then there's another method and another method. There are several methods to find the value of the uncertainty. Let's look at one more method where we find the absolute mean error of the data. So you find the absolute mean error for the whole set of data and call that as the uncertainty. How do we do that? To find the absolute mean error, okay, you find absolute error for each of these data points and then find the average of those absolute errors. What do I mean by that? I will find delta G1, delta G2, delta G3, delta G4, and delta G5. Now, what are these deltas equal to? So, I know that so far we have been calling this G true as 9.81 meters per second square, which is true. However, when we are going to find the error, then that error is with respect to the experimental value, the measured value. So we're trying to figure out how much is the error in the value that we have measured. Therefore, for this case, you're going to look at the average value of G that we have found. So G true is not going to be 9.81 unless the experimental average happens to be equal to 9.81. The experimental G is equal to 9.86. And this is our true value. So true value in this case is going to be average value of G. So in this case, the true value is the average value of G. Let's go ahead and write this down. Get this redundant writing out of my way so I can actually move on to solving problem. G1. G1 is 9.79 minus 9.86. Absolute value. G2, 10.01 minus 9.86. G3, 9.98 minus 9.86, absolute. G4, 9.67 minus 9.86. G5, 9.83 minus 9.86. What do I get? What do I get? We get, and these will all be in meters per second square. The first one gives me 0.07 meters per second square. Then I have 10.01 minus 9.85 will be 0.15. 9.98 minus 9.86 is 0.12. 9.67 minus 9.86 is going to be 0.19. 9.83 minus 9.86 is 0.03. All are positive because we're taking the absolute values. Next, we want to find out delta G bar. Delta G bar will be average of these 5 values that we have just found. So that is going to give us 0.07. Hang on. Okay, clear my calculator here. 0.07, this one, plus 0.15 here, plus 0.12 here, plus 0.19 over here, plus 0.03 gives you 0.56 divided by 5, because we are taking average of these 5 absolute errors. This gives us 0.112 meters per second square. So the answer in the proper form will be 9.86. Okay, let me use a different color. 9.86 plus minus 0.112 meters per second square. Now here's a rule. The uncertainty must be rounded off to the same number of decimal places as is the actual experimental value. So our real answer will be 9.86 plus minus 0.11. Let me go to the next slide. So the answer is this is G, 86 plus minus 0.112 meters per second square. As per the rule, the uncertainty or the error, which is this number over here, must have the same number of decimal places as the experimental average, which is 9.86. So this is going to be 9.86 plus minus 0.11 meters per second square. Now, what does this mean? It means that the actual value, this is going to lie between a range, which is going to be 9.86.11. This is the lowest value of the range when we're using this negative sign, to 9.86 plus 0.11 meters per second square. This time we're using this positive sign. So this really, it's a range. And this will be 9.75 meters per second square to 9.97 meters per second square. So our value lies somewhere between this range. What it is exactly, we don't know for sure. So the smaller the value of uncertainty, the better it is. The less is the random error. Smaller uncertainty implies smaller value of error. Make sense? All right, moving on to the next topic or the next problem. So this is the example of measuring the length of the rod using a ruler. What do you think is the length of this rod? To measure the length, first you have to line up the zero of the ruler with the one end of the rod, and then read the ruler wherever the other end of the rod lines up. So I would say it is about 3.45 centimeters. Do you think you can kind of guesstimate it to 3.45? I think we can. Then we are going to figure out what is the uncertainty in the length L. Okay. So in the case of tools or the instruments that have least count or resolution, we say that as a rule of thumb that the uncertainty equals plus minus the least count divided by 2. Or if you're talking just about the absolute value of that, that is going to be least count divided by 2. Now the least count here is 1 millimeter. 1 millimeter equals 0.1 centimeter. To find the uncertainty, you divide 0.1 centimeter by 2 and you get 0.05 centimeters. So this answer for the length of the rod will be 3.45 plus minus 0.05 centimeters. Now what does this mean? It means that we're saying that the length of this rod is 3.45 centimeters, but we are not 100% certain. We're not sure. All we can say with surety, with certainty, is that the value of the length will lie somewhere between a range, and we can tell the highest value of the range and the lowest value of the range. To tell the highest value of the range, you choose this plus sign and you get it to be 3.45 plus 0.05, which gives you 3.50 centimeters. And to give the lowest value of the range, you have to choose this negative sign here and you get 3.45 minus 0.05 equals 3.40 centimeters. So all we can say is that the actual value lies somewhere between 3.40 to 3.50 centimeters. Where exactly it lies, we don't know. All right. So if I had said that the reading is, or the measurement is 6.25 plus minus 0.05 centimeters, that means the actual value lies between 6.20 minus 0.05, which is 6.20 centimeters, to 6.25 plus 0.05 centimeters, which is 6.30 centimeters. So if you look at this range, which is 6.20 to 6.30 centimeters, if you find out the range, that's going to be 6.30 minus 6.20 equals 0.10 centimeters. That is same as the least count. Correct? So that's what the uncertainty means, physically speaking. I hope that made sense. Anything that you don't understand, please feel free to ask me in the comment section. Time period of a simple pendulum. Okay, let's say the time period of a simple pendulum, you measure it 5 times and your values are 10 seconds, 12 seconds, 9 seconds. We can measure on only integral values, whole numbers for time period, and 11 seconds and another 10 seconds. So we are asked to find the time period T bar. Okay. So we are asked to find the experimental time period. That will be T bar experimental plus minus delta T bar. So we have this simple pendulum. We want to know its time period. To get an accurate data, to get a more reliable data, you will do the experiment some number of times. The more number of times you do, the more accurate your data will be. So let's say you performed this experiment 5 times and this is the data that you got. Okay. To write down the answer in the proper form, you're going to have to first find out the average of these time periods. And that would be T bar experimental, 10 plus 12 plus 9 plus 11 plus 10 divided by 5. What do you get? Okay, let's see. 10 plus 10 is 20, right? 9 plus 11 is also 20, plus this 12. I'm showing you how to easily do it in case you do not have a calculator. Now this is going to give us 20 plus 20, 40. 40 plus 12 is 52. 52 divided by 5. This is going to give us 0.4 seconds. And this will need to be rounded to an integer, which will be 10 seconds. We still need to measure absolute mean error in the time period. That's delta t bar. Alrighty, delta t bar. Okay, so this delta t bar will be delta t1 bar plus delta t2 bar plus delta t3 bar plus delta t4 bar plus delta t5 bar divided by 5. So this is the average of the absolute errors for all the 5 time periods. Now to find delta t1, we need to do, for instance, delta ti. I can be 1, 2, 3, 4, and 5. It's going to run from 1 to 5. It's going to be t true minus t1, absolute value. Same as saying t1 minus t true. Doesn't matter. So in this case, the true value is the average value, which is equal to 10 seconds up here. Okay. So let's go ahead and figure out delta t bar. That's going to be delta t1 bar. So delta t1 bar is going to be 10 for t1 minus t true. So 10 minus 10 plus 12 minus 10, the absolute value of 12 minus 10, plus 9 minus 10, absolute value, plus 11 minus this 10, absolute value, plus this 10 minus this 10 over here, absolute value, all divided by 5. What does this give us? 0 plus 2 plus 1 plus 1 plus 0 divided by 5 is 4 divided by 5 is 0.8 seconds. So our answer would be 10 plus minus 0.8 seconds. And 0.8 will be rounded up to 1. Why? Because 10 has no digit, nothing after the decimal. Therefore, the uncertainty cannot have any digit after the decimal either. So the answer will be 10 plus minus 1 seconds. Moving on to our next problem. The length of a plastic stick is measured 5 times under different environmental conditions, and the results were 10.2, 11.0, 9.7, 10.5, and 10.0 meters. And the manufacturer's provided length of the plastic stick is 10.6 meters. Alright, we're asked to find the absolute error, and here it should really say absolute mean error. Absolute mean error of the data and the relative percent error for the above data. Okay, to find the absolute mean error, let's call it as delta L bar. You need to figure out delta L1, that is the absolute error in the first measured length, plus delta L2, plus delta L3, plus delta L4, plus delta L5, and divided by 5. So this is the mean value of the absolute errors in individual values of length that are measured. So delta L1 will be equal to L1 minus L bar, where L bar is the mean value of length, mean length for all the 5 data points. So let's go ahead and find out the value of L bar. So the average of these 5 values will be, you know how to calculate average. So I'm going to go through this fast. And it's going to be in meters, of course. 5, okay, 10.3. 10.3 meters. That's my answer. Delta L1 will be L1 minus L bar. That gives us, here's my L1, 10.2 minus 10.3 meters, which is 0.1 meters. Delta L2 will be L2 minus L bar. This is my L2, 11 minus, here's L bar, 10.3 in meters, 0.7 meters. Likewise, delta L3 is L3 minus L bar, here's L3, equals 9.7 minus 10.3 meters gives me 0.6 meters. Delta L4, L4 minus L bar, here's L4, 10.5 minus L bar, which is 10.3 meters equals 0.2 meters. Delta L5, L5 minus L bar, here's my L5, 10.1 minus 10.3 meters equals 0.2 meters. Now to find delta L bar, which is the absolute mean error, I have to find the average of these 5. What is the average of these 5? It's going to be 0.1 plus 0.7 plus 0.1, okay, plus 0.7 plus 0.6 plus 0.2 plus 0.2 is 1.8 divided by 5 gives me 0.36 meters. Okay, so our answer here would be 10.3 plus minus 0.36 meters. But following the rules, we have to round off the uncertainty to the same number of decimal places as the actual answer is. So the answer will be 10.3 plus minus 0.4. 0.36 rounds off to 0.4 meters. This is our answer. We were asked to find out the absolute mean error, 0.36. Next, we're asked to find the percent error, which is equal to absolute error divided by true value times 100%. Absolute error equals L experimentals average value minus L true. Take the absolute value divided by L true times 100%. L experimentals average value is 10.3 minus L true. This is the value of L that is given to us by the manufacturer, and that is equal to 10.6. So here minus 10.6. Absolute value divided by 10.6 times 100%. What does this give us? This gives us, so I have 0.3 at the top divided by 10.6 at the bottom times 100 gives me 2.8%. So this is my percent error. There you go, 2.8% error. All right. So I hope that we're making progress with the understanding here about how to get the actual value. The actual experimental value will be the average of all the experimental values. It's equal to the average of the answer or the measurement in all the trials. And to write the answer in the proper form, you need to write answer as that average experimental value plus minus the error or the uncertainty. And to find the error or uncertainty, you will need to find absolute mean error. Here is a related concept. Let's say we do not have a theoretical or a true value for whatever it is that we're measuring. Okay, it might be that I am measuring the diameter of this bottle over here. Okay, And I do not know any theoretical value for this. The manufacturer has not provided me with the diameter of this lid over here. Maybe, it's deformed. And I'm trying to figure out the diameter of this deformed bottle. And I do 2 trials. So I find diameter 1, diameter 2. I find the diameter twice. Now to compare these two values, I will find percent difference between these two. How do I find percent difference? Let's say the diameter 1 is 10.2 centimeters, and that is diameter 1, and diameter 2 is 10.1 centimeters. How do I compare these two? How far off these are from each other? Of course, you can find out simple difference between these two values. Or you could go a notch further and find out the percent difference. Percent difference will be D1 minus D2's absolute value divided by the average of D1 and D2 times 100. So the percent difference in this case will be equal to 10.2 minus 10.1, the absolute value, divided by the average of 10.1 and 10.2 times 100. What do I get? 0.1 divided by 10.3 divided by 2 times 100%. 0.1 divided by 515 times 100%. Now I think I would use a calculator. 0.1 divided by 5.15 times 100 gives me 1.94%. This is the percent difference between these two values of the diameter. Got it? Percent difference will always be between two measured values or between two experiments. So it is absolute difference divided by average times 100%. Easy. Here's the difference between percent difference and percent error. So percent difference is found between two measured values, while percent error is found between measured value or the average of the measured values and a true value, a theoretically accepted or determined value. Make sense? Next, we are going to look at propagation of error in calculations. So far, we have been talking about measuring one given quantity. That was maybe length, or maybe it was acceleration due to gravity, time period, it could be mass. For example, in the case of the plastic stick, we measured the length of the plastic stick 5 times. And after doing so, we found out the average L, which is L bar, and we also found out plus minus delta L bar. So far, that's all we have done. All the problems that we have been solving, that's all we have been doing. We had only one physical quantity, and we did not bother to do any calculations with that. However, in real life, in real experiments, you might measure 1, 2, 3, 4, however many number of physical quantities or values. And then using those values, you might want to add them, subtract them from each other, multiply them, or divide them, right? Now we're saying that each of the measured quantities has an error associated with them. For example, let's say I measured 3 quantities, A, B, C. A, B, C could be whatever. Maybe it's mass, maybe it's length, or it's time. Whatever it is, I don't care. But they will be like this. A bar plus minus delta A bar, B bar plus minus delta B bar, C bar plus minus delta C bar. Okay, so we have these 3 quantities. Depending on what they are, we might want to, let's call this as just A, this as B, and this as C. Maybe I want to find A plus B plus C. Or maybe I want to find A times B divided by C. Now we're saying that A has error equal to delta A bar. B has an error equal to delta B bar. C has an error equal to delta C bar. So whenever we're going to do these calculations with A, B, and C, whether it's finding the summation of these or multiplying or dividing them, this error in the individual values of A, B, and C is going to propagate. It's going to carry itself into the whatever calculations we're doing, the results of these calculations. How? Let's look at that. Let's look at an example of addition. Let's say you have two lengths, L1, it is equal to 5.6 plus minus 0.2 centimeters. And L2 is 3.4 plus minus 0.3 centimeters. You want to add these two lengths up, L1 plus L2. What is it going to be? All right. Now, L1 plus L2, for 1, it's going to be sum L plus minus delta L. Correct? This L over here, that's easy to find. It's going to be just the sum of these two. 5.6 plus 3.4 gives me 9.0. This part was easy, but what is this delta L equal to? We're going to figure that out now. Now this delta L, we're going to find the highest value, the maximum value of this summation. Let's call it as L max. And we'll also find the minimum value of this summation, okay? Maximum value and minimum value. And once we have found that, then we are going to find the range of L, which is going to be L max minus L min, and divide this range by 2 and call this as delta L. How do we do that? Let's look at that. To find L max, okay, I want to use a different color now. Find the maximum value of 1 plus the maximum value of 2. What would be the maximum value of 1 when you use this plus sign here? So that would be 5.6 plus 0.2, which is 5.8. And the maximum value of L2 will be, again, when you use this plus sign over here. So 3.4 plus 0.3 gives you 3.7 centimeters. So this gives me here 9.5 centimeter. Got it? Let's go ahead and now find the minimum value of L. That would be when L1 is at its lowest and so is L2. When will L1 be at its lowest value? When you take into account this or when you use this negative sign. So 5.6 minus 0.2 gives you 5.4, and L2 will be its minimum when we use this negative sign in L2. So that is 3.4 minus 0.3, which gives us 3.1 centimeters. That gives us 8.5 centimeters. So what would be the range? L max minus L min equals 9.5 minus 8.5 equals 1.0 centimeters. So if that is what range is, then what will be delta L equal to? 1.0 divided by 2 equal to 0.5 centimeters. So our answer here will become equal to 9.0 plus minus 0.5 centimeters. So this is the proper strategy, proper way to find the proper form of the answer. But is there a way around it? Is there an easier way to do this? Yes, there is. Let's look at that. 5.6. So for that, let's insert a new slide. We have L1 and L2. L1 was 5.6 plus minus 0.2 centimeters. And L2 was 3.4 plus minus 0.3 centimeters. to find L, which is L1 plus L2, what you will do is, okay, let me rewrite this as L1 bar plus minus delta L1 bar, L2 bar plus minus delta L2 bar, where L1 bar equals 5.6. Come on. And delta L1 bar is equal to 0.2 centimeters. Likewise, L2 bar is 3.4 centimeters and delta L2 bar is 0.3 centimeters. Okay? To find L, which is the summation of L1 plus L2, go ahead and add L1 bar plus L2 bar. First, to get this now, delta L bar. Delta L bar will be equal to delta L1 bar plus delta L2 bar. Simple. Add these two up. So your answer will become 5.6 plus 3.4 plus minus 0.2 plus 0.3. And of course, all of this is in centimeters. Correct? So what if I had more than two values? Let's say I have L1, which is L1 bar plus delta L1 bar, L2, which is L2 bar plus delta L2 bar, L3, which is L3 bar plus delta L3 bar. Keep on going till you get to Ln. N could be 5, it could be 10, it could be 50, it could be 59, it could be 5,000. We don't care. Ln bar, delta Ln bar. Find L such that L is equal to L1 plus L2 plus L3. Keep adding all the n's till you get to Ln. This is going to be equal to L1 bar, so this first value, plus L2 bar, this one, plus L3 bar here, plus so on till you get to Ln bar, this one. Uncertainty would be plus minus, I'll write down here, delta L1 bar plus delta L2 bar plus delta L3 bar, and so on till you get to delta Ln bar. So pretty much all you're doing is adding up all the errors or all the uncertainties. And that would be your cumulative uncertainty for the summation when you're adding the different values that you have measured. And of course, all of these L's, they must have same dimensions. Can't add apples to oranges. Doesn't happen in math. In a real fruit basket, it might happen. You can have bananas, apples, oranges, whatever in a fruit basket. Not in mathematics though. Subtraction. Let's look at subtraction. Why not take the same example? 5.6 plus minus 0.2 centimeters. L2 was, I believe, 3.4 plus minus 0.3 centimeters. Find L, which is L1 minus L2. Okay. To understand this, let's again, okay, but this L, at the end, it will be written as L1 plus minus delta L. But this L at the end should be written as L bar plus minus delta L bar. This L bar is easy. This L bar will be L1 bar minus L2 bar, where L1 bar is 5.6, L2 bar is 3.4. So here you go, 5.6 minus 3.4 in centimeters is equal to 2.2 centimeters. What is this delta L bar? To find out delta L bar, we're again going to look at the maximum value of this L minus minimum value of L, where this is L1 and this is L2. So to get L max, we need maximum value of L1 and minimum value of L2. What is the maximum value of L1? 5.6 plus 0.2 is 5.8. Minimum value of L2 is 3.4 minus 3.3 is 3.1 centimeters. This gives us 2.7 centimeters. L-min. When L1 is minimum and L2 is maximum. When is L1 minimum? When we use the minus sign. 5.6 minus 0.2. 5.4. L2, when is it maximum? When we use the plus sign, which is 3.4 plus this 0.3. 3.7 centimeters. This gives us 1.7 centimeters. Okay. So delta L bar will be equal to L max minus L min divided by 2. 2.7 minus 1.7 divided by 2 is 1 divided by 2. 0.5 centimeters. So quite interestingly, the uncertainty or the error in case of addition and subtraction, where I use same values of L1 and L2, turn out to be same, 0.5. So here this L bar will be equal to 2.2 plus minus 0.5 centimeters. And turns out that the rule for adding up the uncertainties for addition and subtraction is same. In this case, where I had L1 equal to 5.6 plus minus 0.2 centimeters and L2 equal to 3.4 plus minus 0.3 centimeters. L is equal to L1 minus L2 is 5.6. Okay, hang on. Let's be a little more detailed. L1 is L1 bar plus minus delta L1 bar, where these are their values. L2 is L2 bar, where L2 bar is 3.4 plus minus delta L2 bar, where delta L2 bar is 0.3. So when we calculate L, which is L1 minus L2, is equal to L1 bar minus L2 bar, these values, plus minus delta L bar, correct? And this delta L bar will be equal to nothing but delta L1 bar plus delta L2 bar. Fairly easy. So that means if you had 5 L's, where L1 is equal to L1 bar plus minus delta L1 bar. L2 is L2 bar plus minus delta L2 bar. And so on, right? I think you get the point. Li is equal to, hang on, different color. Li equals Li bar plus minus delta Li bar. So I can be 4, 5, and 3. I think you can do that much. And we're asked to find L1 plus L2 minus L3 plus L4 minus L5. What do you think this will be? This will be equal to L1 bar plus L2 bar minus L3 bar plus L4 bar minus L5 bar. So far so good. What about this uncertainty? Uncertainty will be delta L1 bar plus delta L2 bar plus delta L3 bar plus delta L4 bar plus delta L5 bar. Okay. So it doesn't matter whether you're adding or subtracting. Whenever you're doing a calculation, the uncertainty in the result of the calculation is always going to be equal to or greater than the uncertainty in the individual data that you use to do that calculation. So as long as those individual data points have an uncertainty, the uncertainty in the result will always be greater than the uncertainty in the individual data points. That's why these uncertainties are all added up. Make sense? So this is the rule for addition and subtraction. So you can see I have addition here, I have subtraction, both. So this is rule for both of them. I hope that you got it. I'm going to next look into the rule for multiplication and division very quickly, but in the next lecture we're going to solve several examples, several problems based on the propagation of errors. Rule for addition and subtraction. Here, very quick review. Already did it, showed you on the last slide. Multiplication and division. Example. All right, example. Let's look at an example. Let's say A equals A bar plus delta A bar. Okay. And A bar is equal to 5.2 plus minus 0.4 meters per second. B, which is B bar plus minus delta B bar equals 2.8 plus minus 0.2 seconds. Okay. Find C, which is A times B. Okay. Now the C would be written as C bar plus minus delta C bar. This C bar is easy to figure out. That is A bar times B bar. A bar is 5.2 times B bar is 2.8. What does this give me? 5.2 times 2.8 is 14.56, and what would be the units? Meters per second times seconds. Seconds cancel out, it's in meters. For now, I will keep all of these digits in the multiplication, even though over here, in the two terms that are being multiplied, we have only 2 sig figs in each, while this product has 4 sig figs, and it should in principle round off to 2 sig figs to give us 15. That is the rule of sig figs for multiplication. But let's stick with all the 4 for now. We need to next find this delta C bar. For this, once again, find the range of C. C max minus C min and divided by 2. C max. When will you get C max? When A is maximum and so is B. When is A maximum? When you have this plus sign over here. 5.2 plus 0.4 is 5.6 meters per second. When is B maximum? When you have this plus sign. 2.8 plus 0.2 is 3.0 seconds. So seconds cancelled out. Let's go ahead and find out C min. When A is minimum and B is minimum. When is A minimum? When I use this minus sign. 5.2 minus 0.4 gives me 4.8 meters per second times. B min is when you have this negative sign in the B. B minus delta B bar. 2.8 minus 0.2 gives us 2.6 seconds. Seconds cancelled out. So let's go ahead and let calculator do the job of multiplication. 5.6 times 3 is 16.8 meters. 4.8 times 2.6 is 12.48 meters. All right, so what will be delta C bar? 16.8 minus 12.48 divided by 2. What do I get? I get 4.32 divided by 2. 2.16 meters. Okay. So the answer would be here 14C would be 14.56 plus minus 2.16 meters. However, this number over here must round off to 2 sig figs because the least number of sig figs in here in the numbers being multiplied is 2. So this becomes 15 plus minus. The uncertainty must round off to a digit or a number that has nothing after the decimal. So that will be just 2 meters. That's your answer. On this slide, I have shown you explicitly in detail how to find uncertainty when two measured values are multiplied. But things can be far more complicated than this. You may have any number of terms that are being multiplied. We may have 100 terms that are being multiplied, and each of those measured values has its own uncertainty. Then do we really go through all this trouble to find out Cmax and Cmin? Sure we can, especially if you're writing a computer program. Or we could use another method. So the other method is, let's say you have the C, which is A times B. Same thing. C is equal to C bar plus minus delta C bar. That's what we're trying to find out. A is A bar plus minus delta A bar. B is B bar plus minus delta B bar. We want to find this delta C because C bar is easy. So you will say delta C bar over C bar equals delta A bar over A bar plus delta B bar over B bar. So what it really is, this over here is the fractional error in C, or the relative error in C. What is this over here? This is relative error in A, relative error in B. So relative error in C equals relative error in A plus relative error in B. Now we can do another thing here. Here's our equation. Delta C over C equals delta A over A plus delta B over B. Now how does this equation come from? It comes from doing some differentiation with the initial equation. First, you'll have to take natural log on both sides of C equals AB. And after taking the natural log, you will differentiate on both sides. Now, if we're interested in finding delta C, go ahead and multiply both sides of this equation by C. And that will give you delta C equals delta A over A plus delta B over B plus delta C, which is not there. Got to stop over here, times C. Another thing you could do is this equation over here. If we multiply all of this by 100%, what does it give us? Fractional, or the relative error, times 100% gives us percent error in A. Sorry, not in A yet, in C. That is when delta C over C bar multiplies 100%. You get percent error in C. Now this 100% when it multiplies delta A bar over A gives you percent error in A. Plus 100% when it multiplies delta B bar over B bar, percent error in B. Here you go. So this is the rule or the formula for propagation of error in multiplication. Here's another example of finding the area of a rectangle that has a length of 12 plus minus 0.2 and a width of 15.02 plus minus 0.5 centimeters. All right. So here is my length. And width is 15.02 plus minus, there should be 0 over here. Actually, let's go ahead and get rid of the 0 from here. Because the number of decimal places for the uncertainty must be same as the actual value. Find area. Area is length times width, r, right? So finding the first term of the area is easy. It's just 12 times 15.2. What is that? 15.2 times 12 gives me 182.4. And that's going to be centimeters square. But is that all? No. Area will be written as A bar plus minus delta A bar. So far I have figured out this A bar only, 182.4 centimeters square. What is the value of this delta A bar? To find this, you will write delta A bar over A bar equals delta L bar over L bar plus delta W bar over W bar. And then you can multiply both sides by A bar. What does this give me? This will give you delta A bar equals, what is delta L bar? 0.2 divided by 12 plus delta W bar 0.5 divided by W bar 15.2 times this A bar, which is 182.4. Okay, what do we get? (11.8 times 14.7, 173.46. So range divided by 2 is going to be 191.54 minus 173.46 divided by 2. What does this give me? 18.08 divided by 2, 9.04. Same as here. So you can see for yourself that this method works. Alright, moving on to division. Find the average speed of a car that travels 200 plus minus 5 meters in time t equal to 40 plus minus 1 seconds. Alright, so travels distance of 200 plus minus 5 meters in time equal to 40 plus minus 1 second. Find the speed. Okay. So the speed will be v bar plus minus delta v bar. V bar is easy. 200 divided by 40 is 5. Plus minus this delta v bar. That we need to find. So to find delta V bar, again find V max minus V min divided by 2. Okay, V max. When the distance traveled, D is maximum while T is minimum. D is maximum when we use this plus sign over here. So that will be 205 meters. And time T is minimum when we use this negative sign. So that would be 39 over here. Let's go ahead and find out V minimum's formula at least. D is minimum, time T is maximum. D is minimum when we use this negative sign. So it's 195 meters. Time is maximum when we use plus sign is 41 seconds. So let's see what we get for V min. 195 divided by 41. Okay, I'm going to change this color to now. It's a long answer 4.75609. I'm going to just leave it here. Meters per second. That's my V min. V max will be 205 divided by 39. Gives me 5.256. So delta V bar will be 5.256 minus 4.756 divided by 2. What does this give me? Minus 4.756 gives me 0.500 divided by 2, 0.250 meters per second. So, since this answer is 5, therefore this delta V bar, which I found out to be 0.250, should have nothing after the decimal. So when I round this off, it really becomes just 0. See? But before I round it off, it is 0.250. Make sense? Let's look at it using the generic formula, which in this case is same again. So I have this formula V equals D over T, right? I want to find delta V over V. This will be delta D over D plus delta T over T. So it does not matter whether you're multiplying or dividing. Formula remains the same. If I was doing V equals D times T, this will be the formula. If I'm doing V equals D over T, this is the formula to find delta V over V. If I was doing V equals T over D, still the same formula over here. No difference. Okay. Now let's see if this gives us the same answer as we got on the last slide. So delta V will be equal to delta D over D plus delta T over T times V. Okay. Delta D is 5. D was 200. Delta T is 1 and T was 40. And this V was equal to 5. What do I get? Point 0.05 times this 5 over here gives me 0.25 meters per second. What did I have on the last slide? 0.250. Same answer. Same answer. So this is the formula that we could use for multiplication or addition. Where does it come from? Again, in any of these, whichever you're finding the delta V for, you will first take the natural log of both sides and then differentiate it. Not going to get into the details of that, but moving this on. So far, the multiplication and division that we looked at, they did not have any powers involved. But in general, we could have powers, such as in this case, we have powers, multiplication and division. All kinds of things are at play here. So x equals a to the power b times c to the power d over f to the power g. And my goal is to find the uncertainty or error in x, which is delta x. How do I do that? So this power, it comes out and multiplies this fractional error in a, where b is the power of a. Similarly, this power of c, which was d, comes out and multiplies the fractional error in c. And f to the power g, which is in the denominator. But even this comes up as a plus sign, and its power multiplies the fractional error of f. To calculate kinetic energy, the formula is 1/2 mv squared. Now this kinetic energy, when I write it in proper form, has two parts. First is just the kinetic energy plus minus the uncertainty in kinetic energy. This first part is easy to calculate. That is going to be just 1/2 times mass 2.0 from here times 30 squared. That gives me, this is my KE bar, 900 joules, where joules is the SI unit for kinetic energy or energy in general, or work. Alrighty, next I need to figure out what the heck is this delta KE bar. Now to do this, we're going to go ahead and find out KE max, KE min, and go from there. To find KE max, use the maximum value of M, which is 2.0. Okay, you know what? Let's do that. Why not? Let's do it. Where does W come from? KE max. 1/2 maximum mass times maximum velocity squared. KE min. 1/2 times minimum value of mass, minimum value of velocity squared. Okay, 1/2 maximum mass, 2.1. Maximum velocity, 31 squared. Okay. Minimum value of kinetic energy, 1/2 times 2 minus 0.1 is 1.9 times 30 minus 1 is 29 squared. All right, what are these values equal to? The first one, 0.5 times 2.1 times 31 squared is 1009.05 joules. And KE min is 0.5 times 1.9 times 29 squared. 798.95. So delta KE bar will be equal to KE max minus KE min divided by 2. That gives me 1009.05 minus 798.95 divided by 2. All right. And that gives me 105.05 joules. All right. So our answer is 900 plus minus 105 joules. Let's now solve this problem using the formula that we have learned. We know that kinetic energy equals 1/2 mv squared. So we do delta KE over KE. This 1/2 is just a constant. There is no uncertainty in the constant. We know it for sure. It's 1/2. So this doesn't matter. But this M does matter. Delta M divided by M plus 2 comes out and becomes a coefficient of the fractional uncertainty of V. Okay. Alrighty. So delta KE will be, you multiply KE on both sides. Delta M is 0.1, M is 2 plus 2 times delta V is 1, V is 30. Kinetic energy is 900. Okay. We get 0.1 divided by 2 plus 2 divided by 30 times 900. 105 joules. What did we have on the last slide? 105 joules. So the answer is same. Answer is 900 plus minus 105 joules. I think this method is easier. It's more systematic, less chance of making an error over here. It's very straightforward. You can do this way if you want. I wouldn't. I want to know how this works out. I want to know the principle, the logic behind finding the uncertainty. But at the end, I will use this method over here. I'll leave it up to you to choose whichever method you want to use. I've shown you both methods. So I'm going to see you again very soon in the next lecture where we're going to go over tedious, hard problems based on propagation of error.